Alright friends, welcome back. In this video I'd like to go ahead and cover section 2.3 of your textbook, and in this video we're going to be talking about a couple of the different things that we've talked about in the past for how you can analyze the graph of a function. Okay, so we've talked about basically every single topic in this video already earlier in the year, but I would like to go ahead and revisit a couple of things here and just kind of put them within the context of a function, which is the topic of chapter 2. So, talking about domain and range again, remember that there were two key situations that we were always going to be on the lookout for whenever we were taking a look at our expressions. We were looking out for denominators or fractions. We have to say that the denominators can never equal 0. It's never allowed. And we also have to take a look at radicals. So square roots, fourth roots, sixth roots, these are all radicals that have an even index, okay? And so if that's the case, then we have to go ahead and say the part that's under the square root, which remember that's called the radicand, okay? So if you have a radicand, the part under the square root, that's what that's called, the radicand. We have to say that that's non-negative, or in other words, that is either positive or it is equal to 0, okay? And so throughout the video, we're going to be presenting you with a couple of functions, and we're going to be asking you to find their domain and find their range based on either the function formula, in which case we're going to be using these tricks right here, or we might be able to present you with the graph, and we're going to have to kind of review how we go ahead and find the domain and range in that case. Okay, so let's go ahead and find the domain and range of a graph, right? So the directions are simple. It just simply says find the domain and range of the function. And so we've provided you with the graph of that function right here, and some other indicators that tell you what the range is and what the domain is, right? So for those in-person folks, one of the things that we discussed was on the day where we first talked about this is I had some magnets that I went ahead and put on the board, and I put a magnet on each one of these x values here. Okay, and whenever we're talking about the domain, we were simply talking about, which one of these magnets can you drag up or down to touch a part of the graph? Well, I can go ahead and drag this one up. I can go ahead and drag this one up. I can keep that next one stationary. I could drag this one down to touch the graph, and so on and so forth, right? So if you have any one of these magnets that you can touch the part of the graph with, and that's going to be in your domain, all of these magnets that miss as you drag them up or down, those are going to be excluded from your range. Okay, so again, we're only looking at that black curve right there. So if I go ahead and erase the magnets here that don't drag up or down to touch the graph, then we'll go ahead and get a deeper idea of what our domain is going to be. And I want to go ahead and talk about this last one here, right? So if you were to try to drag this up, then the arrow would go right through that hole, and it would just keep going and going and going, and we would never touch a part of the graph here. So for that reason, we would go ahead and exclude that magnet or that x value from our domain, and we'll just simply say that we want all of the x values that lead up to that one. So that'll mean that we have a parenthesis at that x value here, right? So if I go ahead and write the domain out, I might say here script capital letter D for domain. I might say that my domain specifically is going to be between these values, it looks like, of -1. So interval notation, I'm going to go ahead and put a bracket there because I was able to drag that up to the graph. So -1, comma, and then where this this interval ends, right? Well, we said an open parenthesis on that one because, again, we want all of these x values leading up to that, but we don't want to include that itself. It looks like that's going to be an x value of 5 there, which I'll put an open parenthesis on. Okay, so that'll be our domain of this function. So again, I really like that whole magnet analogy, or maybe just thinking about that in terms of dots on the x-axis that you drag up or down to talk about your domain, okay? It's actually the same idea for the range, except here we just want to go ahead and take a look at those magnets on the y-axis, since we're talking about the range now, okay? And so the idea is, again, simple. Now that we're on the y-axis, we simply just want to ask that question, which one of these magnets can you drag to the left or to the right to touch a part of the graph, okay? Well, if we go ahead and take a look here, if we try to drag 5 left or right, we miss the graph completely. So that is going to have to be a magnet that we exclude from our range. It's actually the same thing with number 4 there. That is going to get excluded because I don't touch the function. But starting there at 3, you'll notice that I'm at the very top of that mountain there, okay? And so that will keep. We'll keep 2 because that can drag that left or right to touch the graph. Same thing with 1. For 0, you could drag that to the right to touch, and then same thing for all of these magnets here. But when we get down here to -4, we now reach again a magnet here that if I drag it to the left or to the right, I miss the graph completely. So I'm going to have to exclude that magnet and also exclude -5, and then again all the ones that are below that. So the only question becomes, what is this interval of numbers on the y-axis here that represent the range? okay? Well, the range there would be, again, reading this from the negatives up to the positives, right? Looks like that would be down here at -3, and then from -3, which is inclusive, I'll put a square bracket on that, all the way until we reach a value up here of +3, which is also inclusive. I'll put a square bracket on that. So script capital letter R, and then we're going to say the interval from -3 to 3, including those endpoints because they are filled in on that curve and they're not open dots, okay? So that is a really quick way to be able to figure out what the domain is and what the range is of a given function's graph, okay? And I've gone ahead and done the second one here for you just for the sake of time. You'll notice that, here on this parabola, we do interpret these ends as having some arrowheads, and they do reach indefinitely or infinitely to the left and to the right, so domain is all real numbers there. But you'll notice that in terms of the range, we only start here from the very top of the mountain, which is at a y value of 3, and then we go all the way down to negative infinity there, so making sure to write those intervals correctly, okay? Another concept that we touched on in the past, but it's been a while, is this whole idea of a function being either increasing, decreasing, or constant on a certain interval, okay? I don't want us to get too bogged down by what you're seeing here. This is the rigorous definition of increasing, decreasing, and constant, but the main idea is right here, right? Let's say that you are a part of the graph that is increasing. Well, the way that we define that is we say this. We say as your inputs get bigger and bigger and bigger, so do the outputs. Okay, so basically we describe increasing or decreasing as, the y values are doing this while the x values are doing this. Okay, so while your x values get bigger, your y values get bigger if you're increasing. In the case where you're decreasing, similar idea, as your x values get bigger and bigger and bigger, your y values get smaller and smaller and smaller, and that makes sense if you're decreasing, right? If you are constant, then that means that as your x values get bigger and bigger and bigger, your y values don't change at all. They actually just stay the same as each other as you go throughout. Now, as far as what that would look like on the actual graph, the way that I kind of like to describe this is, say you're on a roller coaster, right? So let's go ahead and draw you on the roller coaster here, right? So I think I did this back in the day here too. So here's you on the roller coaster. Perfect picture. There we go. Perfect. Now, any place on this roller coaster where you are going to be falling down on the roller coaster, that is going to be a place where you are decreasing on that interval, okay? Any sort of flat stretch of road, that will be a interval on which you are constant, and then any interval on which you are climbing up on that roller coaster, that slow anticipation right before you get to the very top of the roller coaster and then fall back down again. Anytime the roller coaster is climbing, that would be an increasing interval there, okay? And so the way that we would express these is with open intervals only, because it's a little bit misleading to say that I am going to be increasing or decreasing at a specific point, because that's not really a stretch of road. That's just a specific location, and it's really kind of open for interpretation if we're going to be increasing or decreasing at a specific point. So for that reason, whenever we write these intervals out, we are not going to use any closed brackets to include those end intervals here. But if I was doing this decreasing interval, that would be the interval from -2 to 0, open. Okay, if I were to do that constant interval, that would be the open interval from 0 to 2. And again, you'll notice that I'm just using the inputs here to describe these intervals, right? And if I go ahead and stick with my coloring convention here on that increasing interval, that's the interval that starts here at +2, and then it looks like it goes all the way until it reaches 4 there. I know that it's going to stop there because it did have a solid dot there at 4 and not an arrow that tells me that this goes all the way up to positive infinity. Okay, so again, we only use open intervals to express these intervals on which we're increasing, decreasing, or constant. Okay, and then this other idea here of those very tops of the roller coaster or the very bottoms of the roller coaster, right? We actually give those a name in mathematics. We call those relative extrema, which is a very fancy name for the following, right? Anytime that you have a minimum on your graph, then that is going to be one of the lowest points on that graph, right? That would be on the roller coaster where you go from falling down on the roller coaster, that location right where you go from falling down to then climbing back up again. That would be a minimum, okay? A maximum on the roller coaster, that would be any place where you go from climbing up on the roller coaster and then you start to fall back down again. So these are basically places where the graph is going to switch from decreasing to increasing if it's a relative minimum. And these would also be places where you are going to be going from increasing to decreasing, okay? So again, relative minimums, those would look like, very bottom locations of any of your curves. Relative maximums, those would look like the very tippy tops of your curves there, okay? So in an example like this one here, example 2, it says find the domain and range, and then find the open intervals where the function is increasing, decreasing, or constant, and then find the relative extrema. Again, relative extrema, all that means is find your minimums, find your maximums, okay? You notice that I've already gotten us started here, and one of the things that I've done here in my answer space is I've differentiated between which one of my answers are intervals. Again, those are ranges of numbers, and which one of my answers are actually going to be locations, so coordinate points. Unfortunately, we do use the same notation for intervals and coordinate points with parentheses and a comma in the middle, so I just don't want us to get confused between one and the other here. So let's actually go ahead and figure out our domain and range here first, right? So I've already incremented this graph. And you'll notice here as you take a look at the curve, if you picture those magnets on the x-axis, I believe because of those arrowheads, we're going to be able to drag those magnets to the curve no matter which input we're at. Okay, so the domain here is going to be all real numbers, which of course in interval notation we just represent by saying negative infinity to positive infinity. We've seen that before. And then again, because of those arrowheads, if you picture those magnets on the y-axis and picture dragging those to the left or to the right, you're always going to be able to find a place of the graph to drag to, okay? And so for that reason, your range here is also going to be all real numbers, okay? So again, we've talked about this before, so I'm kind of just blazing through that explanation there, right? Now for increasing, decreasing, and constant, I like to kind of use some different colors for this. So for any intervals on which I'm increasing, I'm going to go ahead and color those red, right? So let's say that you're on your roller coaster. Let's say you're over here. Here's your roller coaster. Here's you, okay? And you're going to go ahead and take this roller coaster all the way through, okay? So let's go ahead and color those intervals where you're climbing up the roller coaster. Those are going to be your increasing intervals, okay? So that's going to be from all the way down here from negative infinity with that arrowhead all the way until we reach this point right here. And then we change, right? After that, we'll do our decreasing intervals in blue here. We go from increasing or climbing up the roller coaster. Now we're falling down the roller coaster all the way until we get to this location right here. And then now we're starting to climb up again, right? So I'm going to change my colors again. So increasing, that's in red. So I'm climbing up on the roller coaster again until I reach that point. And then finally, I dip down and start to fall again, decreasing. And then after that, it looks like I'm just climbing up again. Okay, and so again, any interval on which I am red or I'm climbing on the roller coaster, that is going to be an increasing interval. So it looks like that's going to be all the way out there from negative infinity all the way until we reach an x value here of, it looks like, -4, okay? So that'll be the first open interval on which I am increasing in this graph, okay? Then I decrease. So again, you talk about this with the inputs there, right? So that would be from -4 all the way until we reach, it looks like I incremented my graph a little bit odd there. Let's just call that 1, okay? So all the way from -4 to +1, that is an interval on which I am decreasing, so I'm going to say that over here. Again, make sure to write these as open intervals with parentheses because we don't want to say that we're including these endpoints on these regions where we're supposed to be increasing or decreasing, okay? Next region on which I'm increasing is going to be from 1 to, it looks like, 3. Again, we're just using the inputs, the x values there. And then after that, that next blue region, that looks like it's going to be from 3 to 5 in blue. And then finally, I have my last increasing interval from 5 all the way reaching out to positive infinity because of that arrowhead, okay? So I think it's a lot easier to kind of think about your increasing and your decreasing regions here by just taking a look at how the graph is incremented and then think about that as a roller coaster using some different colors, okay? You'll notice that at no point on this roller coaster do I actually have any flat road, okay? So the interval on which I'm constant, I'm just going to go ahead and say none here. There's no point on this roller coaster where I just am driving flat. Okay, and now again, those are intervals, so those are regions of numbers. Unfortunately, again, we do use the same notation to write down coordinate points, and so I just want to be clear that when you write down your relative minimums and maximums, again, those are locations where you go from being increasing to decreasing or vice versa, okay? So in other words, all of your relative maximums, we're going to be going from increasing to decreasing. That would be right here, so we'll make those notes there, right? So this is going to be a max, and this is going to be a max. Okay, and then of course these locations here, these are going to be your relative minimums. Okay, so minimum and minimum. And to write these down, we're just going to go ahead and write the coordinates of these points. Okay, and so that first relative maximum, that is going to be at a point with coordinates -4, +2. And then we follow that up with a relative minimum. It looks like that's going to be at a point with coordinates 1, -1. And then the next maximum is going to be at a point with coordinates 3, 1. And then the next minimum is going to be at a point with coordinates, it looks like 5, -2. Okay, so again, I do want to strike that difference because our interval notation is the exact same as our coordinate point notation. So I just want to be clear which is which. Okay, when you're talking about an interval, you're talking about a region of numbers. When you talk about a coordinate point, you're actually talking about the grid and where the location is using your x and your y coordinates there. Okay, the next one I've gone ahead and done for us just for the sake of time in the video. You may want to go ahead and pause and just kind of read through this one and make sure that this one makes sense to you. But I'm going to go ahead and move on here after you have a chance to pause the video to talk about the last topic that we'll discuss here in this video, which is, again, something that we've talked about before, but this whole topic of a function being either even or odd, right? So remember that all this means is it talks about symmetry, okay? So if you have an even function or an odd function, we're just talking about the symmetry of its graph if you were to graph it and look at the picture. Okay, so if you are an even function, that means that you are symmetric with respect to the y-axis. So an easy example of that would just be y equals x squared. Gives you the simple parabola. That is something that is a shape that you could mirror across that y-axis and it would lay on top of itself perfectly. Okay, or you could be odd, which means that you have origin symmetry. So an easy example of that would be the shape of your cubic functions, okay? This would be one where if you were to rotate it 180 degrees, it would land on top of itself, okay? So just kind of talking about the difference between even and odd there. Again, these are ideas that we've discussed before, just kind of reviewing these, right? Algebraically, what that means is this, right? So if you're going to test for even algebraically, what you're going to do is you're going to take your function and you are going to make your input negative. So basically, you're going to be plugging in negative x, and you're going to be doing all the algebra and seeing if what you end up with is just simply f of positive x, okay? So you're basically taking a look at making the input negative and seeing if that changes anything in your function formula, okay? In the case where you are odd, you're going to make your input negative and then see if that's going to make your whole function negative, okay? So algebraically, let's go ahead and demonstrate what that would mean, okay? I did a couple of examples, which we'll take a look at here in a minute, but the directions are simple. It says, are these functions even or odd, or maybe are they neither one, okay? So let's go ahead and test these algebraically. What we're going to do is we're going to go ahead and take our function, and we're going to throw inside negative x, okay? And what we're going to do is we're going to hopefully be able to do all the algebra here and show that this is either going to be equal to g of positive x, or maybe it's equal to negative g of x, in which case we would conclude even or odd respectively. Or maybe we would see that it's neither one, in which case we'll say it's neither. Okay, so let's see what happens here, right? So this function is the function that's programmed to take your input and cube it first, and then take away 5. Okay, of course, the input that we're giving it is negative x, and we just now need to look at the operations that are in this function and decide if this negative right here is something that can basically cancel out for us. Okay, well, unfortunately, it's not, because this negative is being raised to the power of 3, and so what that would lead to is negative 1 times negative 1 times negative 1, which would give you negative 1. It would not eliminate that negative for us here, unfortunately. And so what we end up with here is a function formula that is not equal to our original g of x, and it's also not equal to negative g of x as well. Okay, so what we would conclude here is that g is neither. Okay. Because you can look up above and see that the original g of x was this right here. That was not something that we got right here. These are not equal to each other, okay? And on the same token, if you were to go through and figure out what negative g of x would look like, then that would look like this. It would look like negative x to the third minus 5, distribute that negative in, and you would get negative x to the third plus 5, okay? That is something that is also not equal to what we ended up with here, okay? So again, that's why we're saying neither there, because neither of these things match up to what we ended up getting. We're going to go ahead and say that we'll make that conclusion of it being neither, okay? Next one here is example 3. We have f of t is equal to negative t to the fourth. So again, all we're going to do here is we're going to go ahead and take our function. We're going to plug in negative t, and we're going to see if that ends up changing anything for our function formula here. Okay, so I'm just going to go ahead and plug that in. And so what you'll notice is that negative t is being raised to an even power, so that means that it's going to become positive. So I have this extra negative out front, but then I have positive t there to the power of 4. Okay, and you'll notice that that is identical to what we started with up here. Okay, so f of t is going to be equal to f of negative t, because we ended up getting the exact same result for both. And so what we would conclude here is that f is an even function. If we were to graph it in our graphing calculator, we would find that it does have symmetry over the y-axis. So f is even there. Okay. I already did the next two examples here for us. You'll notice that in example 2, after doing the work, you'll notice that that is odd because we end up with negative h of x there in number 2. And then on number 4, that is another one that is even. Oh, sorry, not even, goodness. That is another one that is neither, I meant to say. Again, because there's no way to cancel out that extra copy of the negative, and there are no original negatives in that original version of the formula there as well. Okay, so again, talked about even and odd before, so just a bit of review. And then finally, what I want to do here is, again, review this topic of finding the zeros of the function. So these would be inputs that cause your function to output the number 0. I already did number 5 there for us. That would be one that I would expect you guys to know how to do already for certain. That's just going to be a polynomial equation. But you'll notice what happens there, right? We are going to go ahead and take your f of x and substitute in its place 0, and then go ahead and solve for those x values here. So we're going to do that same thing for these next two functions, and then we'll call it a video, right? So we'll substitute in 0 for f of x. And so 0 is going to be equal to the square root of 3x minus 14 minus 8. And we're just going to go ahead and solve this for x. So this is a radical equation. We've talked about how to solve these before. So we're just going to simply isolate that radical first. So 8 is equal to the square root of 3x minus 14. Do the radical after we isolate it. And of course, the way we undo the square root is we raise that to the power of 2. So remember, whatever you do to one side, you have to do to the other side. So 8 squared is simply going to give me 64. And then that's going to eliminate that square root on the right-hand side. So 64 is equal to 3x minus 14. And then we can just simply go ahead and start to solve this by getting x isolated, okay? And so in that next line, we're going to have 78 on the left-hand side, and that is equal to 3. And then finishing this up, divide both sides by 3 there. And OneNote is not wanting to be my friend today. So divide both sides by 3. There we go. And I'm just going to go ahead and use my handheld calculator here instead of taking it over to the computer one. So that is actually going to be an x value here of 26. Okay. Now, keep in mind that is an answer that we got from a radical equation, so it always pays to maybe take your answer and plug it back in for x and make sure that you don't end up with anything negative under the square root. So that would be 3 times 26 minus 14. I don't know what the value of that would be, but I know 3 times 26 is a lot bigger than 14, so I'm pretty confident to be able to say that that answer is correct, because we'd be ending up with a positive under that square root if we were to plug back in. So that's pretty good. And then in this last example here, we have a rational function. Again, we've talked about how to solve rational equations in the past here as well, so I'm just going to go ahead and set this up, replace f of x with 0, and then let's go ahead and review how to go ahead and solve an equation like this, right? So really like to be able to do is work with this not as a rational equation, but as a polynomial equation. And so the guy that's causing some trouble is big divided by right here. I have a big divided by 3 minus x. So the way we always get rid of a divided by is, of course, we go ahead and multiply everything by what we were dividing by. And in this case, that would be the expression 3 minus x, okay? So what that's going to do, we're going to distribute that to both the left-hand side and to the right-hand side. And when you distribute that to the left, that's just 0 times 3 minus x. That's just going to leave you with 0. And then on the right-hand side, again, the whole point of doing that was so that this divided by and this multiplied by, those would cancel each other out, and that just leaves you with 2x squared minus 9. Okay, and so again, that's a really easy way to take your rational equation and turn it into a polynomial equation, the rest of which I feel pretty confident that you guys know how to solve, so I'm just going to go ahead and blaze through the rest of this here, and we'll get our final answer. So whenever you're finding the zeros of a function, okay, you're just going to take your output, your f of x, and you're going to substitute in its place 0, and then you're going to solve that equation. Okay, so 9 over 2. OneNote is really trying to play with my colors here today, okay? And then after that, remember that we have to get rid of an exponent of 2, and the way that we always do that is with a plus or minus square root. Remember, anytime you introduce that square root to the equation new, you're going to have to introduce it as plus or minus the square root, okay? And so that's going to give you x is equal to plus or minus the square root of 9 over 2, and remember that we don't want our denominator in the radical, so the way we always handle this is we multiplied the bottom by 2, and we multiply the top by 2. Okay, so just another copy of the denominator itself. So that way we could say that in the denominator, that's just the square root of 2 times 2, and that's just going to be straight up 2. And in the numerator, that's going to be the square root of whatever 9 times 2 is, and of course that's going to be 18. Okay. Now, the 18 is something that you can reduce the radical for, so this will be x is equal to plus or minus 3 square roots of 2 over 2. and that is going to be our final ending result there. So anytime that you can simplify the square root, I would like you to be doing that. Again, we've talked about how to do that extensively in the past, so if you need to go revisit some of those Chapter 2 videos, or not Chapter 2, I meant Chapter P videos, that would be a good idea, I think. Okay? That's going to do it for this video. Again, just kind of reviewing some of the different things that we've talked about throughout the course about how to analyze the graph of a function or expression or whatever you have. So if you guys have any questions, then feel free to let me know, but that's all I have for this one. Thank you very much for your attention, and I'll speak to you in the next one.